Okay, it's my pleasure to introduce Dr. Dillon Dong from NRIO. Dillon's a native of California, went to Pomona College, went to, in between undergrad and grad school, went to Cambridge and worked with Rob Kennicott, working on star formation, and also Eric Murphy, Eric's a long old friend, and Rob Kennicott is a very esteemed member of our community. He's was one of the leaders of the last decadal report. Dillon then went to Caltech, where he worked with Greg Hallinan on the kind of probably the last big survey of the VLA. And he's currently a Jansky Fellow in Socorro, which is where, well, adjacent, as Veronica will correct me, it's not where the VLA is, but it's adjacent. Okay, so let's welcome Dillon, and he's around for the rest of the afternoon if people want to meet with him. Okay.
All right, thanks so much for having me here. So one thing is, I really like my talks to be interactive. I want to be talking about things that interest you. And so if you have questions that occur, just raise your hand or shout it out. I am totally okay with being interrupted. That being said, I do have, as usual, a lot of slides, and I've been told to keep this on time. So we'll see how that balances out. Okay, so today I'm going to be talking about the VLA Sky Survey, which, as Joaquin said, is a major effort being done by the NRAO. And there's a bit of a bonus here, which is I'm going to editorialize a little bit about where I think time domain radio astronomy is going in the next decade. So a very brief outline of this. First, what kinds of transients am I actually talking about? So my interest in the VLA Sky Survey is time domain stuff, right? So slow radio transients, what are they? A brief history of our efforts to find them. How are we currently finding and identifying them? What are the main populations that have emerged out of VLASS? And also looking forward, how can we scale this up? And to what degree do we actually need to? Okay, so what is a slow radio transient? Well, a pretty reasonable observational definition, I would say, is some large and sudden increase in the luminosity of some radio source, right? So I'm going to put much greater than factor of 2 there, and it's going to be occurring on a timescale that is slower than FRB, so not in milliseconds, but potentially minutes, hours, potentially decades. And what can you actually say if you find some source that looks like this? Well, physically, if you have something that is emitting at gigahertz frequencies and it's changing on human timescales, then probably what you're seeing is energetic particles, potentially relativistic energetic particles. If it's high luminosity, 100% it is relativistic energetic particles that are spiraling in magnetic fields. And the most powerful particle accelerators that we see, and the most common ones, are shocks, right? So you have something fast slamming into something slow, and then you get energetic particles being accelerated by diffusive shock acceleration, as in this diagram here with the supernova remnant. But there are also more complex mechanisms that occur particularly in lower luminosity sources, such as magnetic reconnection can accelerate particles. You can have emission that isn't your standard synchrotron or gyrosynchrotron. It's curvature radiation from pulsars. And you can pick your favorite theoretical explanation for what causes FRBs, because I have no idea. At some point, there were more models than actual FRBs detected. That is no longer the case, but there's still a lot of models out there. But the upshot really is, I think that radio transients are interesting because they open a new and unique window into the lives of the objects that actually emit these transients, right? And there's a huge diversity of the kinds of things that we're finding that are associated with radio transients. And if we want to use these windows that are opened up by radio transients, we need to find them, and we need to identify them with those objects, and we need to do so at scale. Okay, so now the history, just one slide on this. There have been efforts for decades to do direct detection or blind detection of slow radio transients. Basically, people take their favorite telescope, they point it at a patch of the sky, and they repeat observations over some cadence at some frequency. And there were lots of upper limits for for decades. Right? In the mid-2010s, we started getting the first consistent detections, had something like 10 detections in the Caltech NRAO Stripe 82 survey. And this early success motivated VLASS, which essentially is just a scale-up of the Stripe 82 survey, but over the entire sky. So VLASS basically is doing, or has done now, 3 full epochs covering the entire sky north of declination minus 40. And it's doing so at a frequency of 3 gigahertz. It has a typically 2 to 3 arcsecond resolution, and it gets down to an RMS noise of something like 140 microjanskis per epoch. And on the bottom is just sort of a very rough schematic timeline for when these epochs occurred. Right? Every 0.1 is coverage of the same area of the sky, and every 0.2 is coverage of the other half of the sky. And the upshot of this is that if you data mine VLASS, you'll find that there's something like 3,500 transients. And this, in particular, as far as I'm aware, is something like triple the number of transients that are not FRBs that are in the literature. There are many exciting results that are coming out of other modern radio surveys that I'm not going to talk about because I'm not nearly as familiar with it. But if you look up what's coming out of VLASS, an ASCAP project, that's really, really cool stuff too. Meerkat's doing some great follow-up with Thundercat, and LOFAR has some systematic searches as well. Okay, so that's the intro. How are we actually currently finding these transients? So I'm going to take you sort of end to end, right? Where we're going to start with the actual observations, and we're going to take you all the way to the transient identification. So the VLA, as I'm sure you know, is an array of radio dishes out in New Mexico. And there's this new mode of observing that was commissioned specifically for the Caltech NRAO Stripe 82 survey that was then generalized to do VLASS over the entire sky called on-the-fly mapping. If you do any kind of cosmology, you're probably familiar with this technique. Basically, the array is just continuously slewing. It's always in motion in this basket weave pattern. Right? It's slewing in RA, and then it goes a little bit in dec, and then it goes backwards in RA, etc. And the way that these observations are carried out is that it slews 10 degrees in RA, and then it does a tile of 4 degrees in declination each time. And effectively what you get for any particular point on the sky is you get a couple of points that are, or a couple of effective pointings that are pretty close to that, and some farther out pointings that contribute a small amount of signal to that. But if you sum it all up, the effective sensitivity that you're getting from this pattern is something like 5 seconds of effective integration per field. So this is extremely shallow, basically the shallowest thing that the VLA is ever going to do. But it turns out that the VLA is sensitive enough that you actually win by doing this because you get a much wider coverage per time that you spend. Yeah?
So this is observing on the fly. The dishes are always moving.
They're always moving. And the way that you compensate for that is that you introduce an electronic delay on the back end, which basically cancels out the movement. Right? And so you're able to electronically point your telescope, essentially. Yeah. The actual implementation of that took a lot of development. Yeah.
Is there a particular configuration that VLASS is done in, or does it go through whatever is already there?
Yeah, it's always done in B configuration, and this is done to maximize the angular resolution, right? So B is the second highest angular resolution configuration, but also not have such a high data rate that it overwhelms the NRAO's ability to process the data, which would have happened if we did it in A configuration. Yeah. Okay, so on the NRAO end, what they do basically is they take the observations, the data from the antennas gets sent to the correlator, which produces raw visibilities, and those raw visibilities go through the standard VLA or VLASS calibration pipeline, which is developed by the pipeline team at NRAO, and it's distributed to our local cluster, managed via HT Condor. And essentially what happens is you get something like 500 gigabytes of calibrated visibilities for every single 40 square degree tile that you take. Sometimes 4 of these are observed in one scheduling block contiguously, and so you get a file of like 2 terabytes or something like that. And so you get that, and then you're basically running the calibration you see, the 500 gigabytes is after calibration. And then you're running imaging, which is the real expensive part, especially if you want to do all the fancy stuff that corrects for the actual annoying things, such as how the Earth is three-dimensional and not two-dimensional. This is called W projection, and is actually one of the dominant causes of astrometric uncertainty, and is not done in the quick look imaging. And you reduce the data volume from something like 500 gigabytes down to 53 megabytes per image. An image is 1 square degree. Right? So you have an order 10 to the 3 factor reduction in your data volume. And that's thankfully where I take over. I don't have to deal with the visibilities. So basically, I take all these images. They are basically the fastest thing that the NRAO can push out. And I run source extraction on that with a pretty standard radio source extractor package called PyBDSF. And basically, I have to take whatever PyBDSF gives me and find transients, as well as the image data, right? So PyBDSF is going to pick out lots of image artifacts. This is very difficult to get around. You can try to change your configuration so that it avoids some of these, but then you start to lose sensitivity. Basically, what I use PyBDSF for is basically just an indication that there might be a source there, and then I post-process after that. Right? And so we have to pick out all the source candidates, and we need to separate them from the clean data. And if we don't do this, then this is what happens. Right? This is a plot from the VLASS pilot survey paper, where in this field, it's become somewhat standard to plot this statistic called the modulation index, which is basically just the fractional variability of your source. And then on the x-axis, you plot like the variability statistic, which is the significance in the presence of noise of your variability. And the thought is hopefully things that are high fractional variability and statistically significant when it comes to noise are mostly transients or strong variables. But it turns out that if you look by eye, only the red points are real sources, and everything else is an artifact in that box. Right? And so you really do need a way to pick out the artifacts. You can do it by eye, but especially if we're going to talk about doing this in the future, this is just simply not scalable. Right. So,
can I ask at the end, how are you doing at the moment?
This slide right here. Yeah, yeah. Okay. So I use the fact that in the radio, the PSF is actually very well known. It's essentially just determined by the position of your source relative to your baselines. And so it's very well modeled by a 2D Gaussian. And so what I do is I just say PyBDSF thinks there's a source there. I'm going to force fit a 2D Gaussian in the shape that I know it should be. And I'm going to subtract it, and I'm going to see if the residuals are clean. Right? And so this basically turns this problem of finding nice point sources. And by the way, physically, a transient has to be a point source unless it's galactic and it's very, very fast. You're just never going to resolve an actual transient extragalactically. So I subtract that point source, and then I test the residuals, right? And specifically, the thing that worked out the best was taking this p-value from this test of Gaussianity called the Shapiro-Wilks test, and just plotting it against the standard deviation of the residuals, because if something didn't subtract out well, the standard deviation is going to be high. And lo and behold, there's this really, really nice separation between things that I classified by eye as real sources compared to things that I classified as artifacts, at least in this test set. There are systematically things that we're missing in this particular kind of processing. So in particular, sources that are sitting on top of diffuse emission are systematically excluded, right? And so I'm working on better algorithms to do this kind of stuff. But at least to the first pass, and because VLASS is so shallow, we don't detect a lot of diffuse emission. This works pretty well. Okay, so all this stuff is automated. And basically what I'm looking for is things that are noise in one epoch and a point source in another epoch. And as soon as I find that, I call it a transient. Right? The point source also has to be bright enough so that it's a significant detection. Yeah.
Before you get too far, can you go back to your plot of eta versus v and explain to me the difference between eta and v? Yeah.
Yeah, so eta is the fractional variability. So it is the difference divided by the mean, I believe. Yeah. And V is how many sigma, like where sigma is your noise, your difference in flux is. Exactly, the signal to noise on the difference. Yeah. When you assume that your noise is Gaussian, which often it's not, right? Especially if you have artifacts. Yeah. Okay. So.
Can I ask something?
Yes.
So on that slide, so what fraction of your computing time is actually spent on the extraction versus the filtering of the artifact? I'm assuming that on the second part, it's going to actually take a little bit longer because you need to be like feeding those 2Ds and then subtracting them and counting the residual. Just wondering if you could.
Source extraction is actually the dominant computational cost in this case, because that also involves fitting. I'm working on an implementation that does not involve fitting. That's basically just taking inspiration from deconvolution algorithms, such as clean, right? And I really like when I can actually write the algorithms myself, because then I can fine tune it to the problem, right? And I'm often able to make improvements on the kind of things that.
And that is because PyBDSF is actually doing a convolution on the fly or something like that. Is that why it takes?
So PyBDSF, what it does is it basically identifies all of the islands of all the contiguous blobs of significant pixels, and then it attempts to fit them with the sum of Gaussians. Right? And this multi-Gaussian fitting problem, as you imagine, is pretty degenerate and requires a lot of computation to do. Yeah. Yeah.
Could I know what's the time interval between each of your epoch?
Yeah, it's about 2.5 years. Yep.
So you're just looking for sources that exist in one detection and not in others, but what about sources that you do see all the time that vary? Do those get included, or you're not looking for them right now? Or?
Yeah, so I don't call those things transients, but I do look for them, right? And the distinction is that if something is not detected in one epoch and is detected in a different epoch, then you're basically guaranteed to have more than a factor of 2 variability. And it's difficult to reproduce that level of variability with things that aren't intrinsic to the source itself. It is possible. Diffractive scintillation does this, but refractive scintillation, which is the thing that affects everything except for compact objects, will typically only give you like a factor of 20 or 30% variability. Your flux scale systematics are typically only going to give you that kind of thing, right? And so it's much cleaner to look for these sharp changes. Yeah. It's not to say that these sharp changes aren't all can't also be variables, right? Particularly the lower signal to noise ones could be things that varied by a factor of 2, which is large, but still happens, and then just poked its head above the noise, right? And that's how it appeared as a transient. Yeah. All right, I think that's all the questions. So let me talk about identification. Okay, so you have found a transient radio source, and you want to now interpret it. There's not a lot of information to go off of. You have a flux, you have a RA and a dec, and that's about it, and a time, right? And you have 2 measurements, one of which is a non-detection. Now we have 3, now that we have 3 epochs. So what can you actually say based on that limited amount of information? Well, you can actually draw a lot of information from specifically the RA and the dec by doing associations with all the super rich multi-wavelength surveys that we have now, right? So, for example, a lot of transients are reported to the transient name server, the IAE repository for all transients, and some of these radio transients are just counterparts to those known transients that are reported from like ZTF or something, right? So here's a type 1c broadline supernova. I'm showing the host galaxy, but here's a classical nova that happened in 2021. Sometimes you're not as lucky. You don't have like a very unambiguous identification of what the associated object is, but you can draw from all the various things that people who study galaxies have developed for identifying what these host objects are. like galaxies and stars, right? So people have done a ton of work into telling the difference between quasars and galaxies and stars, and so we use some of those results. Right? There's increasing spectroscopic coverage of bright sources, and so particularly if something is bright and it is in the SDSS field, then we're likely to have a spectrum of this, right? And so this is just one of them where we have a redshift 3 quasar. Here we just have a galaxy that doesn't have a spectrum, but you look at it and it's a blue fuzz, right? And this is the kind of thing that I would then take to my optical spectroscopic follow-up program and try to get a redshift and try to get potentially late time transient features showing up in the optical, which sometimes you see some interaction lines. In my experience, these kinds of things, and I've shown more carefully in a different paper, that are sitting on star-forming galaxies are very, very likely to be stellar explosions of some kind. So that's context. Sort of part of the frontiers which I'm trying to push in is also using the features from the detection itself, the radio features, to as a means of identification as well. This requires a lot more computation because you can't do this on the images. You have to have access to the actual visibilities, which once they're imaged, the visibilities get deleted because the NRAO can't afford to store them, at least the calibrated ones. And so you have to go back and back process this kind of stuff. But I was able to stream some of the calibrated visibilities to process them before they were deleted in real time, and this summer for VLASS 3.2. And here's an example, for example, of a pulsar that was detected where this is just like amazing spectral features here, right? It goes from basically 0 in parts of the spectrum to 1 Jansky, which is a 3,000 sigma detection, or at least in that, at least compared to the like typical noise, right, in that pixel. So what's the cause of this? This is diffractive scintillation, right? And diffractive scintillation only happens to things that are on micro arcsecond angular scales, at least significantly. And if you see that, then you're basically guaranteed to have a compact object in the galaxy. And so hopefully in the future, I'll be able to systematically back process through the archive and look for new pulsars just using diffractive scintillation. Another feature that you can look for is polarization. Right? So typically the only thing that is imaged is just the total intensity, Stokes I. But here I had my summer student also stream and use our local SLRM to do polarization imaging of all the visibilities before they were deleted. And she found like 5 really polarized stars. Here, in this case, this is the most extreme one, which is actually 99% circularly polarized. And the only emission mechanism that I know of that can produce something like this is the electron cyclotron maser. And so we think that's probably what's happening here. Yeah. So that could be another nice thing to do. That's a future kind of thing, though. I'll mostly be talking about context. So if you want to get the context, you want to have efficient cross-matching against all the various surveys that are out there, right? And you also want to understand how to do that cross-matching. You want to have to be able to make a physical case for why something is or isn't associated, and to have some story that you can tell based on an association or not, right? But for some of the catalogs that are out there, for example, Gaia or Pan-STARRS, if you're like me and you hate writing 80QL queries, you just download the entire thing and you run your cross-matching locally, right? And if you want to do local cross-matching for something that is a catalog of more than of order 10 million entries or so, Gaia has 1.5 billion, for example, then here are some of the optimizations that I found that are helpful. This is by no means the only way to do this. People have worked on this kind of problem a lot. There's, for example, Q3C, which is like a Postgres SQL efficient indexing, but basically everything is some sort of tree query on some spatial index, right? Which turns your cross-matching problem into order log n time per point that you're trying to match, and then you can also, to some degree, vectorize this as well. practically, the main limitation to working with these large catalogs is actually just I/O. If you benchmark your code, your cross-matching code, you'll find that most of the time is spent in actually just loading the data that you need. Right? And so a very useful thing to do here is to shard it in a logical way. Here I'm sharding it by heel picks. So basically by some sort of, by where it's located on the sky in a equal area sort of pixel scheme. Right? And then you can read from multiple different files. You can parallelize this. You can do asynchronous I/O easily. And then if you pre-compute the trees that you're querying to do the cross matches, and you also do your data retrieval of the rows that you care about from these sharded data, then all that can basically mean that your cross-match problem is going to run in like seconds to minutes instead of forever, right? And you don't have to rely on servers being up, and you don't have to learn ADQL. So I think this kind of thing, it's close to solved, how to do efficient cross-matching at the scale that we're encountering in astronomy. And people, I think, are going to make nice web tools to be able to do this. I think there's some wrappers that could be written that makes it a little bit more accessible, but cross-matching is something that is totally possible, even at like the largest scales of surveys. Okay, so the really interesting and challenging thing here, I think, is establishing which associations are statistically significant and also which ones are physically meaningful, right? So when it comes to statistically significant, that's the easier question, I think, where in my mind, the best thing to do is do the same thing that you would do for your catalog, but just do it for a lot more random points, right? And here it's helpful to have a local system too for cross-matching, because you can test as many random points as you want and you're not going to get rate limited by anyone. Right? So here my student Carlos did some cross-matching against Gaia, where we put up like 1 million points in the sky, and we estimated the false alarm probability of a match to some Gaia star as a function of the angular offset from the star as well as the distance to the star. And you can see that basically you can't trust anything in this black region that's up there. Offsets of like more than an arcsecond, and also distances more than like a kiloparsec or so. But smaller offsets and lower distances, here there's an implicit assumption that closer things are more likely to actually be associated, right? Are pretty trustworthy, I would say. And you can see the same thing just in the one-dimensional versus offset on the left. So here's the HR diagram that comes from cross-matching the epoch 2 versus epoch 1. This isn't the full data set. It's something like half of it. And as you can see, as compared to the background Gaia HR diagram, we're not just doing random associations with Gaia, because the distribution of our stars does not track the distribution of Gaia stars at all, right? In fact, it is like all of our stars are predominantly above the main sequence. And there's a physical reason for this, which in some cases means that it is a pre-main sequence star that's falling down one of these tracks. In other cases, it's typically a star that's evolving off the main sequence and starting to interact with a binary companion. Right? And in both of those cases, you start to get really strong magnetic fields, which are the thing that create the strong radio emission. Okay, so that's stars. Cross-matching to more extended sources, galaxies, that's something that I did in my thesis, where here I found all of the transients between VLASS and FIRST. Right? FIRST is at a slightly different frequency. It's a 1.4 gigahertz survey that was done in the 90s and the early 2000s. And so you need to worry a little bit about the spectral index, the shape of the spectrum between 1.4 and 3 gigahertz. But if you set your threshold for variability conservatively enough, then you can avoid all the optically thick rising sources. Right? So I did that. And additionally, I did this isotropic test, but not only did I look for the angular offset, I looked for the offset that was normalized to the size of the galaxy, right? Because galaxies are collections of things, and those things produce light. And if your object is, it really matters when it comes to the offset of your galaxy, whether your galaxy is really extended or whether it is pretty compact. And so if you go and do the visual breakdown of what these things look like, then you find that transients that are far away from the galaxies are actually much more likely to be artifacts. They're much more likely to be associated with like some fuzz that is faint and probably a background galaxy. And if you take out all those contaminants, then you're left with this plot on the bottom with the blue and the green. And you find that basically the line between statistical significance and not in our sample is pretty easily summarized by, is the transient sitting on the light of the galaxy or not, right? Just by visual inspection. So you can actually learn this kind of heuristic. You wouldn't necessarily be able to, like you could guess that, but you wouldn't necessarily be able to back it up unless you did this kind of thing, right? And so here's the sample that pops out. This is basically all the transients that are associated with, all the VLASS to first transients that are associated with SDSS galaxies that have spectra. Right? Okay, so that's a lot of stuff about methodology, yeah.
What's the emission vector?
For what's producing these transients? Yeah, so I make further arguments in this paper where if you look at the exact position, it's kind of hard to see in this diagram, but things that are sitting on red and dead galaxies are predominantly in the nucleus of the galaxy, whereas things that are sitting on blue star-forming galaxies are predominantly off-nuclear, right? It's a split, right? And so this is what you'd expect for things that are in star-forming galaxies to be stellar explosions. It just tracks the star formation of the galaxy. Whereas things that are in red and dead galaxies are something to do with the central black hole. Either it's a TDE or it's an AGN. In some cases, we have clear AGN lines. But I believe in 2 or 3 of these cases, it's colored somehow. Can't really find it here, but if you look carefully at the figure, like number 28, no. I'll look at it later. But there's like 2 or 3 of them that we argued were TDEs just because the galaxy had no indication whatsoever of any kind of AGN activity, right? And there's a spectrum right in the nucleus, completely quiescent. Yeah. Any more questions before I move on? No. Okay. So now I'm going to go through a bit of a highlight reel of some notable populations of transients that are in the full VLASS catalogs. So the thing that I've worked on most myself is stellar explosions. In VLASS to VLASS, we found something like 90 so far. And we also, furthermore, have limits on every single supernova that's ever been detected before those VLASS epochs, right? That's the nice thing about having a sky survey. You will always have a measurement at some late time. And in the radio, this late time is actually meaningful for supernovae of everything that came before. And if you compute the effective volumetric rate, it's something less than 1%, maybe 0.5% or so. And this 90 is something like equal to the number of radio supernovae that are in the literature today. So here's some examples. There are some ones that are very recent, such as this type 2 and this very nearby galaxy, 2024 EHS, that VLASS happened to observe 2 months afterwards. Here we're seeing something that has continually brightened. This is a 1C broadline. We didn't detect it 2 years before explosion, thankfully. And we did detect it 8 months after, and it's only gotten brighter since. So we're past 3 years now. It's continuing to brighten. Some things show up after very, very long delays. Right? Here's supernova from 2015, which 5 years afterwards, in 2020, there was still no detection. It took 7 years to reach the threshold where we started to see it, right? And we see this kind of behavior in TDEs as well. This has to do with the interaction between the supernova ejecta and the circumstellar medium around it, taking time to progress and become luminous, and also for the synchrotron self-absorption frequency to drop to the point where we're no longer killed at 3 gigahertz by self-absorption. We can also use this to find things that are not associated with well-studied objects or like well-characterized whatsoever objects. The first one is just some unknown AT that's reported to TNS, but nobody took a spectrum to classify it. Here's just one that just happens to be associated with a star-forming galaxy. And here's another one of those as well. Right? So in some cases, we just don't know what date it is. In some cases, we'll take follow-up spectra, and we'll find actually that there are late-time CSM interaction features that show up in the spectra themselves. Yeah.
So what's the noise level of the maps, or what's the detection threshold for the transients?
Yeah, so effectively, the noise level in VLASS is 140 microjanskis 1 sigma. In order to call something a detection, I require that it's at least 5 sigma. So you have a 0.7 millijansky effective detection threshold. And in order to call something not a detection, I require that it's less than 3 sigma. In order to really trust it, I require that it's like 7 sigma. So it's something like 0.7 to 1 millijansky or so, if you care about the distinction at that level. Yeah. Any other questions? Nope. Okay. So physically, I think what's going on, and I can go into more length about this, is that VLASS is tracking things on the time scale of its cadence. So it's 2.5 years between epochs. And this kind of slow developing thing tends to be interaction with very dense circumstellar media. Right? And so how do you get the level of density that you need? You pretty much need some sort of binary interaction. No winds will produce the kind of density that will get you the features that we observe. And so this binary interaction, my going theory is that it's some sort of unstable Roche-Loeb overflow, potentially wind Roche-Loeb overflow, or potentially actually just transferring onto the object. And I had a paper in 2021 which argued that one of these events, which we also saw had a jet very early on, that was detected in the X-rays, was a merger between a compact object and a massive star. And so the thing that caused the mass transfer was the Roche-Loeb overflow and then subsequent common envelope of those 2 objects. And then the thing that triggered the explosion was the compact object reaching the core, which there are some theoretical models that predicted this. Yeah. So it's unknown. Yeah.
If you have to guess a possible mass ratio for the binary, which would you guess?
No idea. It is hydrogen rich, right? So that gives you some clue as to the evolutionary state of the star. Like the CSM interaction lines that we saw later on were hydrogen. They weren't helium. So,
or would you have a guess of the primary star's mass?
There's some mass ratio distributions, right, from binaries, and so you can mind your P's and Q's and try to guess that. But I don't think that this is just a general conceptual scenario that I put forward, right? I don't think that we have enough information to really be able to constrain that. But maybe detailed modeling will prove me wrong.
Okay, thank you.
Yeah. Okay. So TDEs, we have something like 1,500 transients that are coincident with galaxy nuclei, and not the majority of them, not even the 30% of them, but like a non-negligible fraction have no indication of AGN activity, either potentially through WISE colors, or in some cases we have spectra that basically look like there's nothing going on at all, at least to my eye. You might correct me, Decker, looking at this spectrum. But it's hard to make the case later on that something is a TDE because you don't have the early optical features that are really diagnostic. You don't have your helium line, right? You don't have your blue flash or whatever it is people look for. But there is some evidence that there are lots of TDEs that do show up at these late times, and systematic follow-up of optically selected TDEs also shows this exact same pattern, where things tend to show up after years, and not in small numbers either. It's like half of all TDEs or something like that. Right? So, there might be a pretty large fraction of these radio transients that are sitting in nuclei that are due to TDEs. And this distinction between TDEs and AGN is also pretty fuzzy as far as I understand. But here are just some examples. I mean, we find things that are reported to TNS as TDEs and are well studied. Right? So here's 3 examples of those. We find things that by other means, Gene Solmawar has really led a lot of this work, we've argued are TDEs. And so the scientific nugget from here is basically that the first kind of radio loud TDE that we found, Swift J1644, is not really representative of TDEs as a whole, even radio TDEs. Most of these aren't jetted. These are much slower outflows, potentially due to disk winds, potentially due to the slower ejecta of the star just like slamming into the circumnuclear medium. And an interesting thing that seems to be emerging is that radio TDEs tend to select for lower mass black holes. We need more like a larger sample size to really conclusively say this, but we're starting to see some systematic differences between the radio selected ones and the optical ones. Okay, so there's AGN. There's so many things that can happen in AGN. This is a very, very incomplete list. My favorite thing is actually you can potentially get weird stellar evolution effects if you drop a star into an AGN disk. People have done MESA simulations of this, and you can get like 1 solar mass turning into 100 solar masses, and that star becoming immortal until it stops accreting, and then potentially exploding. Really, really cool stuff. We don't understand at all what goes on in AGNs, I think. But we find a lot of them. And so hopefully the data will teach us something. Right? We'll be able to find observational distinctions between all these things. There's a bunch of quasars that we're finding out to redshifts of like 1, 2, 3, 4. We're finding lots of more nearby AGN that are studied. Probably a lot of, like once DESI starts to release its full data releases, we'll find a lot of these objects confirmed by spectra to be AGN. This middle one I really like because here in the legacy survey cutout, you can actually see there's a purple dot in the middle of it. And that's actually due to some of the emission from the transient itself being stacked on. Okay. There are lots and lots of these things. In particular, there's lots of these faint red dots that are sort of reminiscent of the kinds of things that JWST is picking out. It's possible that we're seeing beamed emission from far away, like high redshift. It's also possible that we're seeing highly obscured AGN. Right? So that's a mystery. But there are a lot of these seemingly hostless transients. So here's just a deep field at 27th mag. And in some of these cases, like in the central one, we find pretty clear like red dots right here, which you would just never be able to detect in something like pan-stars. Right? And in some cases, you can go at least as deep as legacy, something like 25th mag, and still see nothing. Right? So I think the jury's still out as to what these things are. Potentially high redshift, potentially highly obscured, and potentially galactic compact objects, which in some cases we do find. Obviously this classical nova is a galactic compact object, but here we have another hostless transient that is a well-studied low-mass X-ray binary flare and absolutely nothing in any optical imaging survey. Right? And also, of course, pulsars, right? If they don't have a bright binary companion, you're never going to see it in the optical. So in particular, we have found something like 600 known pulsars. And this diffractive scintillation thing, I think, is the thing that we're going to be able to use to identify the ones that aren't known pulsars. There's also things that are just in very crowded fields, things at low galactic latitude, some extremely bright ones, like look at this NVSS versus VLASS transient, which was less than 2 millijanskis in 1995 and 70 millijanskis in 2017, right? A whopper of a transient. But even the second one, like this thing at galactic latitude of very close to 0 is just nothing, just purely in VLASS, and then it's 13 millijanskis. Okay, so I think galactic transients are some of the most mysterious ones that are out there. The Milky Way in particular contains like 10 to the 8 compact objects. You know, if you have one compact object for every 100 solar masses formed, then you're going to get 10 to the 8 just by forming the galaxy. And we have something like 500, 600 known pulsars that have been detected, and we're going to be looking for new ones. Right? And a lot of this galactic transient work is being led by Caltech grad students Jesse Miller and Delina Levine. Okay, and the last population I'll be talking about is radio stars. So there's been an explosion of recent work, particularly coming out of Australia, of these radio stars that are being detected in ASCAP. And we're finding lots of these in VLASS as well, right? So here are just some examples found by Carlos. So we have a flare from a known T Tauri star. We have one from an arcseconds Venn binary, and we have a M-dwarf flare right there. Right? And we have things that increasingly, when there's great coverage of the galactic plane, we're going to find things that just happen to be in the test field. Hopefully, at some point, we'll find one that has a nicely sampled light curve at the actual time of the transient. Right? And my student Taya from the summer found some ones that were highly polarized, and the polarization fraction is quite diagnostic of the emission mechanism when it comes to stars. So here's, again, the HR diagram that we have. Something like 50% of them are close binaries. Something like 30% are pre-main sequence. Something like 10% are M-dwarfs. This is very different from lower frequencies. ASCAP is dominated by M-dwarfs, but it has to do with the magnetic field strength on the surface of the star. We can use further radio processing with more computational power to do better diagnostics, but we're not there yet. And basically every wide field sensitive radio survey in the future is going to find these, right? We're just going to keep building up our catalogs of radio stars that are out there. Okay, so the last thing I'll talk about is how do we scale this up? So VLASS has already increased the slow radio transient detection rate by a factor of 100 relative to the historical efforts. Next generation radio telescopes should increase this detection rate by another factor of 100, maybe even 1,000 if you're optimistic. So we're going to be able to, we're going to have huge data streams coming out of these, right? And we're going to have increasingly rich amounts of contextual data to cross-match against from things like Rubin and things like DESI and Spherex, and potentially complicated cross-matching problems from poorly localized things coming out of LIGO, IceCube. Right? So we're going to want to establish good ways, and there are a lot of people in the optical community as well that are doing this kind of work of establishing these associations. And we're going to want to do it in a streaming way. Right? When it comes to the radio, so far the biggest bottleneck really is the initial data processing. So if you take all the stuff that the NRAO does, reducing this 500 gigabytes down to 50 megabytes per image, this actually takes something like 3 weeks as it's currently implemented. It's not a very efficient implementation, but it is still in large part CPU limited, whereas many other parts of it are really just like IO limited. For example, per image, my entire transient pipeline end-to-end takes 3 minutes. Right? So, there's no point optimizing this part until we've gotten the actual processing of the radio data down, right? And so there's a major effort in the NRAO algorithms R&D group to develop efficient algorithms that aren't packaged as some sort of thing that you just can't directly call in CASA. And in particular, there's been a large focus as of late for GPU acceleration of the most critical bottleneck, which is gridding. Essentially, lots of convolutions, right? And it's part of imaging. In the future, I think that we'll also want to do more efficient I/O, and we'll want to store our radio visibilities in more efficient formats so that it is easily, it's thread safe when you read it, right? And it's stored in a way, it's sharded in a way that can be distributed so that it's parallelized over, large clusters, right? Potentially, containerized clusters orchestrated by something like Kubernetes. And one of the things that we'll want to do is really fix some of these memory bottlenecks as well in these algorithms. So lots of like CSE kinds of things. That's the biggest bottleneck. The rest of the stuff, it's not scale that's the problem. It's really that we need to develop good techniques, I think. Right? So right now with VLASS, I'm dealing with images that by and large look like the left here. There's like, if you zoom out, there's nothing there, right? It's mostly just noise. Whereas in the future, every DSA 2000 image is going to look like the right one, and we're going to have to deal with the same things that optical astronomers have to deal with when it comes to crowded fields. But in some cases, DSA 2000, we might be able to do image subtraction. With the SKA, with the NGVLA, we probably won't, because we're not actually, we have different UV coverage for each of these images. And so you're just going to get lots of artifacts if you try to do image subtraction. So probably we want to invest in something like computer vision. We want to parallelize this because the source extraction process is local. Or you want to split up the images into patches and then distribute that as well. Cross-matching, as I said, is pretty much close to real-time streamable already. And the things that we want to do are the things that are already outlined. We want to pre-index these trees. We want to have trees that are extensible and periodically rebalanced so that we can accommodate new sources that are to these catalogs. Like Ruben's going to continually be discovering new sources, and we're going to want to cross-match all of them. Right? And we're going to want to, again, shard the data in a way that makes I/O efficient, because oftentimes that's the bottleneck. But really, I think the biggest thing is data access for people who don't want to think about this kind of stuff is maybe the biggest area of improvement that I think we can do as a field. Again, this is me editorializing. But we have lots of VO tools that are out there. But you have to write ADQL queries, right, to access it. So maybe we want to have large language models generate these queries for us automatically in the future. Or maybe we want to wrap that all up in a GUI, right, so that your 70-year-old advisor who still programs in IDL can do this, right?
I'm not even 70 yet.
Outing yourself, I see. Yeah, and really, we want to make data accessible so that people can actually focus on the interesting questions here, right? What are the things that make cross-matches significant? What are the scientific stories that we can get out of associations between this, we're going to get a multi-wavelength picture of every point of the sky. We'll need to have some framework for interpreting that, right? And also, this is, I think, the part that AI will likely struggle with for the longest, right? And so we want to maximize our human efforts and not make people spend their time learning how to use tools. Okay, so this is my last slide, really. But this is my contribution to this. We were criticized in VLASS for not having good data access. In particular, the cutout server was often timing out. And so I wrote my own cutout server. And we got the access time per cutout from timing out for 100 cutouts in 5 minutes to 100 milliseconds per cutout. Right? And so pretty soon I'm going to build in a fits download API endpoint where you can just send a post request to the server, or you can copy paste all these coordinates into the box. And then you can just click a button. You can download all the fits cutouts that you want from VLASS. It's not just going to be VLASS. This kind of thing is easily extensible to the entire NRAO data archive. And so, any publicly available image that's in the archive, you'll be able to search and access just in this easy and intuitive way, or hopefully intuitive. So this demo is basically just showing the execution speed. I copy pasted in some sources from my transient catalog. And this front end basically makes queries not only to my server, but also to other ones that I was able to find that are out there. They're also well written, such as the legacy one, the wise one, et cetera. All right, and that's it. Thanks for listening. I'll take any questions.
Thanks. This is all very cool. I was curious about what you had done with the real-time spectral processing. Obviously, the pulsar is fascinating with the distillation. But for other things like the TDs or AGN, are you able to pull out like a spectral index within the VLASS band or anything like that?
Yeah, so basically what we're doing is we're just stacking visibilities. Like we're phasing them up to a particular point, and then we're just stacking everything at phase equals 0. Right? So we essentially get arbitrary resolution, and we can just choose the binning. Right? And so if you want your bin to be 2 points, we can do that. If you want it to be 4, we can do that too. It's just how much signal to noise do we have to work with.
Have you found anything interesting in those for those other sources, like weirdly steep indices or features?
I haven't been able to do this at scale yet, but I will be, yeah, at some point.
Yeah, at the beginning of the talk, you said that the VLASS pipeline doesn't do W projection and it introduces some astrometric errors. How do those compare to the size of the PSF?
They're smaller than the size of the PSF. So the typical scale of the astrometric uncertainty is like half a arcsecond or so. And the size of the PSF is like 2.5. Yeah. So it's not like, huge systematics. You can, if you see an image, you can trust the location for the most part. It gets worse near the poles, right? And at low declination as well.
Is there any merit to ALMA follow-ups of any objects in your survey?
So oftentimes radio transients evolve so that the high frequency stuff comes first and then the low frequency stuff comes later. But there's some things that are just going to be emitting at all frequencies, right? So like if we find some sort of, if we're prompt about finding like a new X-ray binary that's turned on, absolutely go follow up that with ALMA, right? But you have to have some sort of physical story for why you're doing this kind of follow-up. Yeah.
Playing off of that, do you ever do like lower frequency follow-up?
Yeah, so my standard suite of follow-up, at least for the stellar explosions, is 1 to 10 gigahertz or 1 to 12 gigahertz spectra, right? Because there's a selection bias where you're going to find things that are peaking in your band because that's where they're brightest, right? And you're sensitive to the largest volume. And so oftentimes, if you're able to find the peak, that's the most informative feature that you're going to get if it's a synchrotron spectrum. If it's not, then by all means, like go find all the features you can, right? But the peak and its evolution are the most useful thing.
Any other questions? Let's thank Dillon again.